So now that we've reviewed second derivatives in Calc 1, let's talk about how to take second derivatives if we have multiple variables in play. So how do we define second derivatives in multivariable calculus? Well, the second order partial derivatives of a scalar field on n variables is notated in two different ways. One way we can do it is with this fraction notation. We write curly d squared f over curly d xi curly d xj. And what this means is that we will take the partial derivative with respect to the ith variable after taking the partial derivative of f with respect to the jth variable. So in the denominator here, we're working our way from right to left. We can also use my preferred notation, which is the subscript notation. This is f sub xj sub xi. What this means is that we first take the partial derivative of f with respect to xj, and then we take the partial derivative with respect to xi. So we're doing two partial derivatives in sequence here. Now, both of these are referring to the same thing, so these two notations, even though they look different, are referring to the exact same process. First, we differentiate with respect to xj, which, if we're using this quotient notation, is the rightmost variable in the denominator, and if we're using subscript notation, it's the variable that's closest to the function. Then we differentiate with respect to the other variable, xi. So if you know how to take partial derivatives, you know how to take second order partial derivatives. So let's look at an example here. I'm looking at the scalar field f of xy, so this is on two variables, and this is equal to sine of x minus 3y. Well, if I take the first order partials, there's only two of them. I could take the partial derivative of f with respect to x. That ends up being cosine of x minus 3y. I could then take the partial derivative with respect to y, and this ends up being negative 3 times cosine of x minus 3y. Here I needed the chain rule. But now I could use these two first order partials to construct all of my second order partials. So what's my first, let's see, the first one I did here was f sub xx. So to construct the second order partial with respect to x twice, that means I take the partial derivative of f sub x with respect to x. Well, f sub x is cosine of x minus 3y, and when I differentiate cosine of x minus 3y with respect to x, I produce negative sine of x minus 3y. The next second order partial I calculated was f sub yy, so that's differentiating f sub y with respect to y. Well, f sub y is negative 3 times cosine of x minus 3y. When I differentiate again with respect to y, this should end up being negative 9, so times sine of x minus 3y. So I get negative 9 times sine of x minus 3y, again using the chain rule. So the chain rule pops out a negative 3, but then the derivative of cosine is negative sine, of course. I can also construct what's called the mixed second order partials. So this one I'm doing is f sub xy. This says to take the partial derivative with respect to y of f sub x. Well, f sub x was cosine of x minus 3y. When I take the partial derivative with respect to y now, I'll get a factor of negative 3 times negative sine of x minus 3y, which ends up being 3 times sine of x minus 3y. Another second order partial would be f sub yx. This is telling me to take the partial derivative with respect to x of f sub y. Well, f sub y is negative 3 times cosine of x minus 3y. When I differentiate with respect to x now, I should get negative sine of x minus 3y times negative 3, which ends up giving me 3 times sine of x minus 3y. So I had two input variables, which means in total there are 4 second order partials. One thing to pay attention to here, though, is that fxx was negative sine x minus 3y, f sub yy was negative 9 sine of x minus 3y, so those two are different. But then f sub xy was 3 times sine of x minus 3y, and f sub yx is 3 times sine of x minus 3y. So in this situation, fxy was the same as fyx. And it turns out that that's not a coincidence. This always happens, as long as our function is nice enough, which for us they always will be. And this is what's called Clairaut's theorem. Clairaut's theorem says that the second order partial of f with respect to xi and xj is the same as the second order partial of f with respect to xj and xi. In other words, the order doesn't matter. If you differentiate with respect to I and then, or with respect to xi and then with respect to xj, that's the same thing as differentiating with respect to xj and then with respect to xi. So as long as you know which two variables you're using, it doesn't matter which order you do them in, so it's hard to make a mistake.